We will now come to the analysis of rolling. So, in this why we need analysis of this rolling process, the mechanics of rolling, we have to look at it. There are various things which one has to look at it. When you are plastically deforming the material, you wanted to know what is the capacity of your rolling mill. What are the forces which are generated, because the metal is passing through between two rolls. It is similar to what you can see in like in our roadside, no, the making the sugarcane juice, no, that is also like the sugar canes are passing through this two rolls, and then it gets squeezed in between, and the other person take it from the output and again bends it and put it into the inlet and other things. All those things are there. There he is not adjusting the roll gap, rather he increases the thickness and other things. That is the thing. But a stage may come where the roll may not be able to rotate, because if the pressure requirement is very large. And but in industrial purpose, when you are going to do the rolling operation of metals, the forces which are going to be developed are very high. The stresses which are going to be developed are very high, because it is the compressive stresses in the roll gap or in the deformation zone that will have the reaction of that will result in the roll separating force. The roll separating force may come. So, if there is the roll separating force, if it is very high, then what will happen is that your dimension of the work put after it comes out will not be what you wanted. It may be less, it may be more. Okay. So, these problems will come. Second, the pressure or the forces are very large, the roll deflection may take place. Deflection on the along the radius also, deflection along the length of the roll also can take place. So, you may find that the thickness of the roll is not uniform. So, all these matters comes into picture, but more important that what is the roll separating force which is going to come, what is the torque which is required for the motor for this rolling operation. These are the most important thing. Then other characteristics comes like what is the friction effect which is coming, whether you want an external force to allow the metal to move into the roll gap, or whether the roll itself can draw the material out. So, all these things can be analyzed. So, for that we have to look at the mechanics of rolling operation. So, this is the typical case of a of the rolling which we are finding it out. So, these are two counter rotating rolls. So, one is here, and the metal is entering into this roll gap. Okay. So, before proceeding further, we have to assume certain things. The first assumption, the rolls are straight and rigid cylinder. So, it is rigid. We are assuming that the rolls are rigid. It is not going to deflect. Any type of deflection, we are ignoring it in our assumption in this when you are discussing about this mechanics. Now, width of the strip which you are going to roll, the width, that means which is perpendicular to this screen is much higher than the thickness of the sheet. Okay. So, it is much higher than the thickness. That means you have the, and in that condition there will not be any widening. Okay. So, since the width is very large compared to thickness, there will not be widening, and you end up with the conditions of plane strain. So, plane strain deformation we can assume in our analysis. The coefficient of friction mu is very is low, and it remains constant when the metal moves from here to here till the from the inlet to the exit. The coefficient of friction is a constant, though in actual case it may not be, but this is one assumption we are taking. And the yield strength of the material remains constant. We are assuming that okay, there is no work hardening, but we can take that by assuming a average flow stress and doing our calculation. Okay. So, as long as the reduction is not very large, then this will be a reasonable assumption for our analysis. But still, if you are considering the work hardening phenomena, that also can be considered without any problem in our analysis, that can be done. But for simplicity, we are assuming that yield strength remains constant. Now, certain things are there. You are allowing the billet to enter into the roll gap. The billet is moving with a velocity V I, and the billet is having an initial thickness T I, and it is entering into the roll gap with a velocity V I. The rolls are rotating counter-rotating rolls, they are moving with a circumferential velocity of v, and this v is higher than vi. And after the material gets deformed, after it gets rolled, it comes out with a velocity which is Vf. So, you will find that the velocity keeps on changing from inlet to the outlet, the velocity keeps on changing. This is because the moment it comes in contact with the roll and a small amount of deformation is taking place, as the thickness reduces, there is no increase in the width. That is our assumption, plane strain condition, there is no widening. So, it is only whatever height is reduced, correspondingly the length of the billet or the strips keeps on increasing. Okay. So, from here it was having a velocity Vi. When the reduction comes, the metal has to move with a slightly higher velocity. So, as with the more and more deformation taking place along the deformation zone or along the roll gap, the more and more the velocity keeps on increasing, velocity of the workpiece keeps on increasing. So, finally, when it comes out, you will find that the velocity is much higher than the inlet velocity. So, outlet velocity of the strip is much higher than that of the inlet velocity. But all these things are happening when the rolls are moving at a constant velocity of v, that is there. So, this v, so when initially the velocity is less and we found that it keeps on increasing as it moves through that, but at some point in the roll gap, you will find that the velocity of the strip is equal to the surface velocity of the roll. Okay. So, that is condition. So, there the roll velocity and the strip velocity is same, and that point you call it as the neutral point. Okay. And then beyond the neutral point, the velocity of the strip will be higher than the velocity of the roll. So, but before the neutral point, before means from exit, from entry to the neutral point, the velocity of the roll will be higher than the velocity of the strip, whereas after from the neutral point to the exit side, the velocity of the billet will be higher than the velocity of the roll. Now, when that is happening, and we are assuming that there is friction, though coefficient of friction is less, but frictional forces are coming into picture. So, because the metal is compressed and there is a friction which is there, and the friction will always try to oppose this moment of that. So, in that case you will find from the inlet side of the roll to the neutral point, you will find that the direction of frictional force, the mu p is something, and from the neutral point to the exit of the rolls, the frictional forces reverses. So, these things are there. So, in this what we are showing here, the frictional force which is coming here is the region before the neutral point. When I say before the neutral point in rolling analysis, because our analysis when we start, we are starting from the exit and moving towards the inlet. In analysis, that is what is done. So, what comes is that from the exit to the neutral point, you will find that the direction of the coefficient of friction, frictional force will be as shown here. But if it is from the neutral point to the inlet side, it will be the reverse direction. Why? Here you will find the velocity of the roll is higher than the velocity of the strip. So, naturally the velocity frictional force will be in this direction from the inlet side to the neutral point, because there the velocity of the roll is higher. But whereas from the neutral point to here, you will find the strip velocity is higher than the velocity of the roll. So, in that case this will have in the opposite direction, that means it will be in this direction. Okay. So, that is the so this point one has to be very clear. The direction of the frictional forces reverses when it crosses the neutral point. Now, in this case, though it may not be required, but when you are doing this analysis, we will assume there is a back tension at the inlet side and there is a front tension at the exit side. So, back tension represented by sigma xi, and at the front side it is sigma xf. And for our coordinate system which we are going to consider, the origin of the coordinate system will be at the center of the line, center to center line joining the roll center. So, that is it will be here, and our x direction is taken towards the right. So, these are our coordinates. With respect to that, we will be discussing the things. Now, for our analysis, let us take an elemental strip of this, and in a enlarged view it is shown here. What are the, so let us look at the free body diagram of this strip. So, because it is continuously being deformed, so your sigma x is along this direction, and because there is a difference in the axial stresses. So, here you are getting at the outside of the strip, you are having sigma x plus d sigma x, and then at the roll metal interface you are having this frictional force mu p. So, there is a compressive force which is coming, which is normal to the strip. So, at an angle with that you are getting the pressure P. So, this is the, and the width of your element is dx, and initial thickness Ti we are taking as a, if you take that, that is we are equating it into as is equal to 2y. So, Ti is equal to 2y. So, we are taking similarly here Tf is equal to twice y plus dy. So, that is the thing. So, this is a simple element on an exaggerated view when you are taking it. This is what. So, let us now go to the equilibrium of forces on the element in the x direction. So, I will just draw it here, so that this part will be clear. So, when you look at the equilibrium of forces in the x direction, you can write this as 2 into y plus dy into sigma x plus d sigma x minus 2y into sigma x minus r d theta mu p, because if you resolve this along this direction, for this p as well as mu p, if you resolve it, mu p cos theta plus, because two surfaces are there, that is why this is coming as 2r plus 2r d theta p sin theta is equal to 0. So, we are taking this along the x axis direction, and if you just look at it, since theta is very small. So, when theta is very small, we can say sin theta tending towards theta and cos theta tending towards 1. So, we can write it in this form. So, 2 into y plus dy into sigma x plus d sigma x minus 2y into sigma x minus 2r d theta mu p, d theta is 1, mu p into theta into 1 plus 2r d theta p into theta is equal to 0. So, if you just neglect these higher order terms, this can be simplified into 2 and eliminate these things, whatever common things and other things, 2y into d sigma x minus 2y into sigma x minus 2r d theta mu p plus 2r p theta d theta is equal to 0. So, with rearranging, we can write it in the differential form as d into y sigma x minus r into p into mu minus theta into d theta, that is equal to 0. Remember, the direction of the mu is what we have shown here is for the case from the before the neutral point, that means mainly in the exit side. This direction is for the exit side, that you should have it in mind. Okay. So, that should not be confused. And since friction force is assumed to be small, the principal stresses in the element can be taken as sigma x. So, since mu is very small, because you will find that in this mu the value of mu will be somewhere around less than 0.2, 0.3 and other thing. So, since mu is very less, is small, the principal stresses are sigma 1 is equal to your sigma x, and sigma 3 is equal to minus p. This minus sign comes because it is compressive, and you can also write that sigma, in that case sigma 2 will be under plane strain condition, it will be a half into sigma x plus minus p. So, that also will come. So, now if you apply the von Mises criteria to this, applying von Mises criteria, you can write that sigma x minus half into sigma x minus p, that is sigma 2 from our previous equation, whole square, that is sigma 1 minus sigma 2, okay, plus sigma x minus p plus p, that is sigma 2 plus sigma 2 minus sigma 3. So, that is what, whole square, plus sigma 3 is minus p minus sigma 1, that is sigma x, the whole square is equal to 6 k square, where k is the shear yield strength, uniaxial shear yield strength of the material. So, from this if you do, you can write it as, it comes to say 1 by 4 into sigma x minus p, the whole square, plus 1 by 4 into sigma x plus p, the whole square, plus p plus sigma x, the whole square is equal to 6 k square, plus 6 k square. So, that finally on simplification you will arrive at a p plus sigma x is equal to 2 k. This is the final. Applying the von Mises equation, you will get equation 2 as this, and if you look at the equation 1 as this. Now, from using this equation 2, eliminating sigma x in 1. So, we can just write that equation as d by d theta of, see, sigma x is equal to, that is sigma x is equal to 2 k minus p. Is equal to 2 k minus p into y minus mu minus theta into r p is equal to 0. So, this is our equation number 3. Remember this sign, okay, of mu. Now, when we said, see, like the direction of the frictional forces from the entry to the neutral point is one direction, and once it crosses the neutral point, you will find that the direction of the frictional forces changes, it reverses. So, to take care of these two across the, from the inlet to the outlet, we can write in a general form that you can add d by d theta of 2 k minus p into y we can write this as minus of plus and minus mu minus theta into r p. So, is equal to 0. So, remember that in this case positive sign for the region from neutral point to exit and negative sign from entry to neutral point. So, that is why this plus or minus, you take any one of that only, depending upon which region it is. Now, when you look at that, as the metal is deforming from the inlet to the outlet, it undergoes deformation. Two things are happening. One, the thickness keeps on reducing, but when the material is being deformed, there is a work hardening which is taking place. Okay? So, when the work hardening is taking place, your value of the shear yield strength keeps on increasing. But total load, now we can assume it is almost remaining constant because k into y, if you just take it as, we can have a reasonable assumption, to a great reasonable assumption, we can assume that k into y remains constant, because when k is increasing, y is decreasing. So, it is a good assumption to assume that the product k into y remains constant. So, we can write this equation number 4 in that case as 2. This is equation number 4. So, this equation number 4 can be written as two ky into d by d theta 1 minus p by 2k plus theta minus plus, this minus sign we are changing it, into mu minus or plus mu into r p is equal to 0. So, that we can write it as equation number 5. So, that is what we can write it in this form. Why? Because k increases with the reduction due to work hardening, y decreases with the reduction hence k into y is a constant, which is a reasonable assumption. So, okay. Now, all these things, this positive and negative sign, one shouldn't be knowing. Now, as theta is very small, see, whatever you do, that reduction is there, but in actual case, when you look at the theta value is very small, if especially when the roll diameter is very large, you will find that theta is small. Okay. So, in that case, we can write that we can have an expression between the thickness and the this one as T f by 2 plus r theta square by 2, since theta is small. Okay. So, now this equation number 5, if you expand it and substitute the value for y in this. So, we can write it like this, that is and remove all these other parts and other things. So, and on simplification we can get it as minus of T f plus r theta square into, because that is 2 ky, into d by d theta of p by 2k plus 2 into theta minus plus mu into r into p by 2k is equal to 0. So, this is what we are getting, or that is we can write it in this form in terms of p by 2k. So, that is d of p by 2k by p by 2k is equal to 2 r into theta minus plus mu into d theta divided by T f plus r theta square. Rearranging it, we will get this relationship. This equation, let us integrate it. So, when we are integrating it, we can write it as integrating the above equation we will get integral d of p by 2k by p by 2k is equal to integral of 2 r theta d theta divided by T f plus r theta square minus or plus integral 2 r mu d theta divided by T f plus r theta square. This is equal plus constant C 1, where C 1 is a constant of integration, where is equal to a constant of integration. So, this integrating we can write it as log p by 2k is equal to log T f plus r theta square, very straight integration, minus plus 2 mu root of r into 1 by root of T f, sin tan inverse when it is coming, that is why tan inverse root of r by T f into theta, plus we can write log C by 2 r. So, C is another constant. So, this will lead to the equation. If you take the anti-logarithm, we can write it as, that means it can be written in this form p by 2k, that is the non-dimensional pressure p by 2k is equal to C into y by r into e raised to minus or plus mu lambda, where lambda is equal to 2 root of r by T f tan inverse root of r by T f into theta. So, if you just come that p by 2k, same equation I will write it, p by 2k is equal to C into y by r e raised to minus or plus mu lambda. So, we can apply that at the beginning of the roll, applying equation 2 at the beginning of the roll. The change, the sign change you should know, that is P plus sigma x is equal to 2k. If you substitute here, in that what we will be getting is P I. So, for inlet, I refers to inlet. So, that we can write P I. Okay. So, P I by 2k, P I by 2k, this suffix I refers to inlet, okay, is equal to 1 minus sigma x I by 2k, where P I is the roll pressure, at the roll inlet point. So, if you use this into equation number 6, this is equation number 6. So, substituting in equation number 6, we can write it as P I by 2k is equal to 1 minus sigma x I by 2k is equal to C minus, let us say C minus, because at the inlet thing is there. So, that is equal to T I by 2 r into e raised to minus mu lambda I. Lambda I means especially at the inlet point, that is why we are putting that lambda I. Okay. So, here we can put e raised to exponential e raised to, where lambda I, it is similar to our lambda only. Lambda I, we can substitute it as, get it by 2 root of r by T f into tan inverse. It is only difference in the theta, that is the only difference. So, if you put it as root of r by T f into theta I. So, that is what we are getting. So, this C value is the value of the constant before the neutral point is reached, and C negative is the value of constant before the neutral point. So, one should remember that this theta I, when we are taking this, we should not forget. Theta I is taken because this is our this one. Now, this is the direction at which theta I is taken. Okay. So, it is not from the inlet to the outlet, it is from the outlet to the inlet. So, that one should keep it in mind when you are taking the theta I value. So, that is why. So, before the neutral point means it is at the exit side. So, from this we can find out the value of C minus is equal to, that is C minus is equal to, say just 2 r by T I into 1 minus sigma x I by 2 k into e raised to, because this minus will come now plus mu lambda. Now, for this point beyond the neutral point, that means from the inlet side to the neutral point, there also you have a different C value. So, that you have to calculate it. So, for that, for point beyond the neutral point, for points from roll inlet to the neutral point, equation 6 can be written as see sigma xi is your back tension what we are giving. Okay. So, that is what we are. So, if you apply can be written as say like that, if you just say that P f is equal to P f by 2 k is equal to 1 minus sigma x f by 2 k, where sigma x f is the front tension we are going to. So, in that case you can just where P f is the roll pressure at the exit. So, that means 1 minus sigma x f, 1 minus sigma x f is equal to. So, that we can say 1 minus sigma x f by 2 k is equal to C plus T f by 2 r. This is the, instead of T I you have to use T f here. Okay. So, that is the thing. So, from that now that is you will get C plus is equal to 2 r by T f into 1 minus sigma x f by 2 k. So, this is your equation number 9. Equation number 8, this is equation number 8. So, substituting this we are getting the value of the constant before and after the neutral point. So, the our generalized equation, if you look at it, we can just using this C minus and C plus, we can write two equation using these values of C plus and C minus from equations 8 and 9 respectively. In equation we can obtain dimensionless roll pressure P by 2 k for the regions before and after neutral point as P by 2 k before is equal to 2 y by T I into minus sigma x I by 2 k into e raised to mu lambda I minus lambda, equation number 10, and P by 2 k after means after the neutral point is equal to 2 y by T f into minus sigma x f by 2 k into e raised to mu lambda. So, you are getting this the value of the dimensionless roll pressure. So, once from the you calculate it, you multiply by this 2 k, you get the value of the roll pressure at any point at any angle theta defined by your lambda. In the lambda now the theta value is coming. So, for that particular value you can find out what is the value of the lambda and then get it. Okay. So, these are the two dimensionless equations which you are getting. Next we will also find out how to determine the value of the neutral point also. So, that will be in the next lecture. Thank you very much.